so far, we've only dealt with situations that are ideal. In this whole course, we've only dealt with situations that are ideal. In other words, we don't deal with messy forces like friction or drag. In other words, non-conservative forces. So far in conservation of energy, we've had two examples where we focus on a nice conservative force like gravity, right? Where it's very easy to track the energy from beginning to end. But what happens when you do take into account friction and drag that eat up some of the energy of an object, okay? How can you deal with that? And so for the first time in this course, I'm going to teach you guys how to handle friction and drag when you're exploring the motion of some object in the world, okay? And the object in the world is going to be this little penguin. And she starts out with a velocity of 6 meters per second. Then she slides down here and then swoops up to the tippity top over here. And whatever energy she has left, okay, is going to be gobbled up by some friction surface here until she comes to a rest at some distance d. And the problem is asking you, how long is this d, right? How long is she sliding before she comes to rest because friction takes up all her remaining energy there, okay? So how do we deal with this? Okay, so a couple things we know. We know she starts with 6 meters per second. We know that the frictional coefficient of the surface is 0.6. We also know that this height over here is 1.1 meters, okay? And so we're going to solve this problem exactly the same way we would any other conservation of energy problem. And how do we start any conservation of energy problem? We start with E1 equals E2. Okay? So in other words, the energy that the penguin starts out with over here in the initial situation is going to be equal to the energy that she ends up with, right? Including the energy that she gives away because this frictional force is doing work on her. Okay? So in other words, all her energy here is being converted into all this energy and work done by friction over here. Okay? So remember, the second step of any conservation of energy problem is to decide what energies you have in the initial and final situation. Well, in the initial situation, she has what kind of energy? Just kinetic, right? So I'm going to put kinetic energy here. And you could say that, yes, she has some potential energy above this surface, right? But it's fine to just call this H equals 0, okay? Because we're only concerned about her position relative to where she starts, and she's rising this level. This part doesn't even come into play, okay? That's what's so powerful and amazing about conservation of energy. Whatever happens in between, so long as there's no friction down here, but whatever happens in between, it doesn't matter. All that matters is initial and final, okay? And so we can call this H equals 0 and this up here, H equals 1.1, and say, for now, there's no potential energy here, okay? So she has kinetic energy initial, okay? And that is totally fine. So what kind of energy does she have over here? Well, she has climbed up to a certain new height, so now she does have potential energy, right? Sorry, that's going to be potential energy 2. And whatever remaining kinetic energy she had is actually being siphoned off, lost, because friction's slowing her down until she reaches her rest position over here at 2, okay? So it's not that she has kinetic energy over here because she comes to rest, but what happens is, remember, work is energy, and work from friction is what remains, right? So she starts out with this kinetic energy, she gains, that turns into a little bit of potential energy, and whatever else is left over turned into the work done by frictional force, right? So all that kinetic energy turned into work and a new potential energy. Okay, so this is the trick. This guy right here is how we handle non-conservative forces when we're doing conservation of energy. And you'll see how it plays out in a second. So next, third step is we substitute our equations. Kinetic energy is, of course, 1/2 mv squared, right? Potential energy is, of course, mgh This is V1 H2, right? And then remember, work is force times distance, right? So this is going to be the frictional force, coefficient of friction, times the distance that the penguin moves, okay? But we know that the frictional force, right, is just mu kn, right? And we also know there's no other forces acting on the object, so we have, use another color here, we have normal force pointing up, right? And we have weight going down. So this is one of those cases where the normal force is equal to the weight, which is equal to mg. Okay? So we can say that the frictional force is mu times m times g. Okay? So let's go ahead and substitute that in. Now that means we know that 1/2 m v1 squared equals mg h2 plus mu mg d. Again, super satisfying. We have all these m's that can just be canceled out, canceled out. That's not always the case when you have a frictional force, but in this case it does work out, so that's nice. Always make sure, though, that the mass is in every single term if you're going to do some canceling, okay? And then all we want to do is solve for d over here, okay? And so just do your algebra. 1/2 times v1 squared, we put our v1 in, which is 6, times g, 9.8, times h2, which is 1.1, times mu, which is 0.6, times g, which is 9.8. Solve for d, and I get the magical answer of, what do I get? What do I get? Oh, I get a magical answer of 1.22 meters. Okay, so this penguin was sliding for 1.22 meters once it reached the top position here. Okay, so once again, the middle doesn't even matter, right? It would matter if we were trying to find the velocity of the penguin when it slides down here, because then that would be our 2. But that's not what's happening. We only care about the endpoints, okay? We have a penguin that starts out with a certain kinetic energy. It swoops down up, right? Ends up with a little more potential energy, and then a whole bunch of work that friction does on the penguin, right? And so that kinetic energy turns into potential energy and work. And using that equation for work, we can solve for exactly how long the penguin needed to slide before it came to rest. Okay? So this is your first introduction to how to deal with non-conservative forces in conservation of energy problems and in physics in general. We know how to deal with friction now.